Hey everybody, today we're going to be talking about the Triboelectric effect, its history, mechanism, and most importantly the Triboelectric series. Now the Triboelectric effect, when you look at its root word components, tribo comes from the Greek word meaning to rub, and then electric obviously has to do with electricity. It's named the rubbing electric effect because in ancient days it was noticed that when you rubbed a piece of silk on a piece of amber and you pulled them apart, the amber and the silk would actually be attracted to each other. That's why we have the current word for electron. That was actually the Greek for amber. For a long time, people have noticed that, okay, amber and silk, those both have an attractive effect when they're rubbed against each other. People started to discover other materials that would have the same kind of effect. Leather, aluminum, steel, silicon, hair. Some materials, when you rub them on other materials, would then be attracted to each other. For a long time, the mechanism wasn't completely understood. People had some guesses that perhaps it had something to do with electron transfer, perhaps ion transfer, maybe it was a transfer of the actual material, maybe you rubbed off a little bit of the amber on the silk or vice versa. Recently, we actually confirmed by Kelvin probe microscopy and triboelectric nanogenerators that it is indeed electrons that are being transferred. We looked down at the atomic level and we were able to see the effect of the electrons moving about, and they were actually able to use the charge that's transferred to power some teeny tiny little generators on the nanoscale. The mechanism for this is pretty straightforward. It's very easily observed at a day-to-day scale. If you take, for example, a piece of wool and a piece of PVC, the law of conservation of charge states that there is an equal amount of charge and finite charge in the universe. And as far as we can tell, that's equal. So at rest, before we do anything, there's an equal amount of positive charge and negative charge on both the PVC and the wool. So because charge is conserved, when we rub them together, we don't actually gain or destroy charge, we just transfer the positive charges onto the wool and the negative charges onto the PVC. The reason that's the case on an atomic level is the wool is actually donating some of its electrons from the orbits of its atoms to the PVC. So the PVC ends up with more electrons. Again, charge is being conserved, it's just that charge is now unequally distributed. So there's a different amount of charge between the wool and the PVC as they feel an attractive force. Now, the question is, why is it necessarily that this one gets the electrons and this one gets the positive charge, in this case being carried by the protons in the nucleus of the atom? Honestly, we don't know, but we have been able to quantify which ones receive the positive charge and which ones receive the negative charge. And we rate them from the materials that get most positively charged to the materials that get least positively charged in what's called the triboelectric series. Now, the key feature of the triboelectric series is not that you have to have a positive material interacting with a negative material. The key takeaway is that there has to be just an absolute difference in where they sit on the triboelectric series. So we go over here to our demonstration table. We have here a couple of different materials. We have some glass, some aluminum, some wool, some PVC, and of course my hair, which we're going to be using today. And then over here we have some little colored styrofoam pellets. These are very light. If there's any charge present on any of these materials, they'll be attracted to that material. So if we look here, we would guess that we would have, since there is a decent amount of separation between PVC and wool or cotton, we'd expect to see a decent attractive force both when we rub the PVC pipe on my shirt, which is made of cotton. See the little beads hopping up onto it. And about an equal amount of force when we rub it on the wool. If you listen closely, you can kind of hear the crackles of the static electricity discharging. There we go. A little bit easier to rub with the wool. Additionally, hair is even more positive in the triboelectric series. So we'd expect to see an even stronger effect when we rub the PVC with the hair. I did this a couple of days ago when my hair was a little bit greasier. It worked a lot better. Dry hair is not quite as effective, but you should still be able to see some effect. There we go. Look how far they hopped up that shaft. All right, now here's the interesting thing. If we went and we switched out our PVC pipe for something like glass, and we rubbed that in my hair, since there's very little separation between hair and glass on the triboelectric scale, you're going to see a much smaller effect if we see one at all. Let's see if the little beads even move at all. Not even shifting. A little bit on the ends, maybe just a little bit. However, if we take the glass and we rub it on the wool, that's not as far removed as the PVC was from my hair, but it's about the same absolute difference from wool as PVC was from wool. So we'd expect to see about the same effect. There we go. Look at all those little guys. Now, finally, if we were to take wool and rub it against aluminum, which are exactly on the same level of neutral, at the exact same point on the triboelectric series, we would expect to see absolutely no effect. There's not going to be any separation of charge. As you can see, those little peanuts aren't going anywhere. All right, I hope you guys learned something today. We've come a long way from rubbing amber on a piece of silk. We now understand that it's the electrons being stripped off of the atoms and being transferred to another material that causes the triboelectric effect, and we're able to quantify exactly how strong this effect will be by placing different materials on the triboelectric series.